Chapter 5, Ethernet, Introduction to Networking. Here's your objectives. So Ethernet is one of the most widely used LAN technologies today. It's defined by the 802.2, 802.3 standards. It supports 10 meg, 100 meg, a gig, 10 gig, 40 gig, and up, 100 gig. It operates at data link and the physical layers. Ethernet relies on two separate layers of the data link to operate, the LLC and the MAC sublayers. LLC handles communication with the upper layers and is implemented in the software. So the MAC constitutes with the lower layers and implemented in the hardware. So we have copper, wireless, and fiber. So those NIC cards are all separate and they're responsible. So the MAC sublayer is responsible for data encapsulation and media access control. So frame delimitation is the start and end of the frame. The addressing would be the source and destination MAC address, and the error detection would be the FCS or the CRC, and we'll talk about those just in a minute. And media access control is responsible for placing the media, the frames on the medium or on the media, and also remove those. Ethernet has been around since 1973, and it's always been evolved and faster and more flexible than most of the other technologies. Earlier versions were started at 10 meg, and today we're operating at 10 gig and up. So your frame field for encapsulation looks like this. So your fields are preamble, which is the start, destination, source, MAC address, Ethernet type, which is going to be your upper layer protocols like IPv6, IP in routing protocols, and then your data and in your FCS. If a frame is small, it's too small and a collision has occurred under 64 bytes, it's called a runt and will be discarded. And if frames larger than 1500 are considered jumbo and baby giant frames and will also be discarded. So a hacker could use that technique to actually flood the layer 2 devices with too big or too small frames. So the MAC address is the primary identifier at layer 2, and it's a 48-bit, 12 hexadecimals, and it should be a review 0 through 9, A through F. You should be able to convert hex to binary and then to decimal. The MAC address has 48 bits, 24 is the unique identifier for the vendor. So you can see that 00602F represents Cisco, made the NIC card, and the other 24 bits is the unique identifier for the particular device. And there are 48 bits. So if you look, you have 6 sets of hexadecimal of 2s. The MAC address is burned into the ROM or burned in address, and it's a ROM chip, so it can't be changed, but we know the software can. And I believe the new Android iOS allows you to change your MAC address randomly for positive reasons, not like a hacker would do for negative reasons. When a device is forwarding a message to the Ethernet, it attaches the MAC address so it knows where to send it. And the destination address is always listed first and then the source. If you'd like to see your MAC address, go to your PC on the Windows machine, do ipconfig all, or you can do MAC in a Linux of ifconfig or IP space address works also. These are the 3 ways we can represent hexadecimal. It's with 2 digits and a dash, 2 digits and a colon, or 4 digits with periods. A unicast is 1-to-1, so we will know the MAC address of the destination. So 1-to-1, most efficient method to move data. A broadcast, many protocols need to use broadcast, like our DHCP and our ARP. DHCP gets your IP address. ARP will resolve a known IP to a MAC address. And the IP address for a broadcast would be all ones in the host section, which in this example was 192.168.1.255. And the subnet mask on this would be 255.255.250. So the 255 is the last number in the range of the IP address. And if you're going to do a MAC address, it would be inspected at layer 2, and it would be all Fs. Or another common broadcast would be 255, 255, 255, layer 3. Multicast starts in the IP range would be 224 to 239. If we know our subnet mask, we know 128, 192, 224, 240. So 224 to 239 is a range within our subnetting. And the multicast address starts with a 01005E at the layer 2. And if we convert that, zeros are all zeros. We put it into a nibble. The 1 would be 001. 00 is all zeros. 5 would be the 4 and the 1. And then E would turn into 8, 4, and 2, making it 14. A lab for identifying and seeing MAC addresses. Layer 2 switch makes forwarding decisions based off the MAC address. When the switch is powered on, has an empty MAC address table, or we call it a content addressable memory. And we know that Ethernet is a listen and wait technology, so if no traffic is generated, the table will stay empty. Learning MAC addresses are dynamically, so the switch examines incoming frames and records the new source MAC address on each port. If the MAC address is unknown, it is added to the table with the port number. If the MAC address exists already, it will update the timer, and by default, Ethernet switches will keep MAC addresses for 5 minutes, and your PC will age out or forget your MAC addresses in 300 seconds. Process to forwarding to destination MAC address. If the MAC address is a broadcast or multicast, it will be forwarded out all frames except the one that was received on. If the destination MAC address is a unicast, the switch will look it up in the table and switch it to the port for the exit or egress. And if the MAC address is in its forwarding table, if the MAC address is in the table, it will be forwarded the frame out to specific port. And if the MAC address is not known in the table, the MAC address is not in the table, the switch will forward the frame out all ports except from the incoming frame as a multicast, which is a technique that hackers can use to flood layer 2 devices with broadcasting. Filtering frames. When a switch populates this table, then it remembers the MAC address to the port. In this example, we have ports 1 and 4 in the MAC address table, and ports 2 and 3 evidently have not generated any traffic, so therefore their MAC addresses are not known. They must have been aged out. Another video, which I'll do in my demo. There's a lab to do. And then we're talking about forwarding frames. There's 2 methods we use: store and forward, which means it receives the entire frame and also reads the CRC, which is the error detection. And CRC stands for check redundancy cycle. So it's just a mathematical computation we'll talk about in a little bit for error detection, but not correction. And then we have the cut through method, which reads the most minimal part of the frame, which is the first part of it. It'll read the destination MAC address and then forward the frame without reading any of the contents or checking for errors. So the cut through method, there's two cut through methods we use: fast forwarding and fragment free. Fast forwarding receives the least amount of frame information, reads the MAC address, and sends it. Fragment free will read up to the first 64 bytes, therefore having a little bit better of if the frame has been damaged or not, but not do the error detection with the FCS. So fast forward just reads the minimum, sends it. Fragment free will read up to 64 bytes and send it. If fast forwarding doesn't work and it's too many error detections or collisions, it'll switch to fragment free. If you still have that many, then you're going to switch back to the store and forward method for the error detection. Memory buffing, we can do port-based memory buffing, we can do shared memory buffing. Port-based would mean that the switch would allocate each port a specific amount of memory equal, and then the shared would be a common memory buffing area. So port-based you'd want to use if you know your data frame rate is consistent with all your end devices. Shared memory would maybe put it with a server, which is going to need a lot more memory because it has much more layer 2 traffic on it. So we either can go full duplex or half duplex. I don't think we see anything in half duplex today except for fiber because we need 2 lines of that. And so if you have a duplex mismatch, what'll happen, the link will go turn off, it'll disable. But we don't worry about that too much anymore because we have auto MDIX, because like devices will need a crossover cable, but auto MDIX will automatically switch the ports to be 1 to 3, 2 to 6 for a crossover cable. And also you can do detection of speeds, so you won't have a mismatch duplex any longer. ARP. So 2 primary functions of the addressing for the Ethernet LAN is a physical address and a logical address. So we can see the physical address is going to be the MAC address. The logical address will be the IP. So if the MAC address is on a remote network, the MAC address will change at every layer 3 device. If it's on the LAN, the MAC address will stay because it doesn't have to go through a layer 3 device. But if you want to leave your LAN, your gateway will be the MAC address, and then you can see that R1 forwards it out the interface, and we'll do this also in one of the labs. Introduction to ARP. So we have Ethernet frame, and it has the destination and the source. And if you normally start communication with an IP address, so whatever layer 7 application you're using knows the IP and then needs the MAC address. So it'll send out a broadcast saying who owns this IP, what device has this IP, and that responding device will give back the MAC address. And all other devices on the network will just ignore the frame. So ARP functions, it's in the ARP table, and it's in cache memory, and it goes into the RAM, and it's mapped to an IPv4 address. So as the ARP process happens, IPv4 is known. It says, anybody have this IP address of 192.168.1.7? And then the responding device says, that's me, here's my MAC address. Good videos to watch. Also make my demos. So you can remove the ARP table because if something dramatically changes in the network, you want all your devices to flush out the MAC addresses, and also, especially for Wi-Fi, you want your access points not to hold on to the MAC address as someone's traveling across your campus or your network across campus or across the buildings. So you can manually remove them, and Windows system keeps the ARPs in for 2 minutes, because you can imagine how much layer 2 traffic you generate, and it would fill up your memory, possibly. On the router, your ARP tables look like on the left. You see your IPs and the hardware address, and on the right would be your PC. And you can see if it's either dynamic or static. And there's another lab. ARP broadcast. So when you send a layer 2 broadcast, it goes in switch, and the switch sends it out all ports except the one it was received on. ARP spoofing is when you change your MAC address. So if a man in the middle, like in this example for the hacker, is going to redirect you to his PC, and it will give you a false MAC address and the IP to match it. So it's a common technique that's used, but if you're in an enterprise level, your switches will mitigate techniques known as dynamic ARP inspection, or DAI. Here's your chapter summary.